That's really good. Okay, awesome. Hi, my name is Ilana. I'm an MIT alum from 2019, then did a 2-year MNG, and today we'll talk about dialogue systems. So it's a wide field that covers use cases from chatbots to task-oriented systems, and also architecture from rule-based one to ChatGPT that went viral a month ago. A lot of this talk will follow Jarabsky's book, chapter 15 in the new edition. So on outline, we'll talk about human conversation and try to appreciate some of the difficulties that come up in analyzing it. Then we'll talk about chatbots, then task-oriented systems, and then end with a forward-looking discussion about LLMs. So human conversation, why is it hard to study? Um, Turn taking is one such reason. So, you know, you can tell in a conversation, let's say between two people, they take turns talking, and when one is done saying an utterance, the other needs to realize that and then start talking himself. Also, when I'm talking, I might be interrupted, and then I need to know to like stop and then let the other say their utterance. And also, multi-turn conversations tend to have grounding, so information previously stated gets repeated so that everyone stays on the same page. Um, Dialogue acts are another property of human conversation, and it refers to this idea that different utterances might serve different purposes. So, for example, I sometimes might, offer my partner information, such as when I was born or, when I need to travel. I might ask someone to do something for me or, more politely request information as a question. I might make a commitment or I might make a joint commitment for both of us, or I might just acknowledge receiving some information. Now, conversational analysis looks at higher order structure in conversations. So one such higher order structure are adjacency pairs, where, in a conversation, I expect that a question would be followed by an answer, or a proposal by an acceptance or rejection, or a compliment by a downplayer. Um, Another higher order structure are subdialogues. So they usually take some examples of sub-dialogues are corrections or clarifications. So for an example, this would be a simple two-turn exchange that might become more complex once a sub-dialogue appears. So, in this case, the second person gets interrupted, and then there's a correction sub-dialogue going on, and then the conversation backtracks to scheduling a flight. Initiative is another property of human conversation, and it's easy to understand if we look at interviews. So, in an interview, the reporter holds control of the conversation, and the interviewee replies. That's not the case in most conversations. Usually, they are mixed initiative, which is hard to replicate in software. However, if we choose not to, then that can lead to frustrating experiences where you've probably seen talking to an IVR or like voice bots where you get stuck when the bot wants some information from you and cannot extract it. The conversation does not proceed. Um, Inference and implicature are another property. So it refers to this concept that if I'm asked a question, I don't always explicitly answer it. So in this example, if I'm asked, when I want to travel, and I say, oh, I need to be somewhere on the 12th, then I expect my partner to understand I want to travel the day before. Um, so all these things, turn taking, grounding, dialogue acts, higher order structures, initiative, and inference, all these things make it hard to reason and mimic human conversation. So now moving on to chatbots, it's a field people have been interested in for a long time. So since Turing in the 50s, this is a seminal paper from Alan Turing where he introduced the concept of like chatbots and his Turing test, which is this ideal that we'd want to build machines that we cannot distinguish from humans, or intelligent machines. Um, Chatbots come in a variety of forms. They can be rule-based or they can be corpus-based. The early ones were rule-based, and some example of rule-based systems are ELIZA from MIT and Perry from Stanford from the 60s and 70s. So ELIZA was a simple rule-based system that acts as a Rogerian therapist, and it's easier for it, if you want to pass the Turing test, a good strategy is to mimic the situations where you don't need a lot of knowledge about the word, because a therapist can ask rhetorical questions, and that's normal for them to do so. So this is an example of a successful conversation with Eliza, and it's pretty impressive, right? Right? If you read it, I could see a therapy session going like this, I guess. Fire is a follow-up to ELIZA. It has the same kind of rule-based patterns, but it models a patient that has schizophrenia rather than a therapist. And it does so by keeping a model of its own mental state and some variables to keep track of its anger, fear, or mistrust. And it's the first chatbot to pass the Turing test 50 years ago. Now moving on to corpus-based chatbots or more modern approaches. They can be subdivided into information retrieval systems and natural language generation systems. So looking at retrieval ones, when I have a dialogue turn queue that I need to respond to, I make use of an index of conversations, and I retrieve from that index, I retrieve the most similar term to my query, and then can reply. Does that make sense? Any questions? Also interrupt me if there are questions. On some similarity search, yeah. So sometimes I can retrieve an utterance as most similar to my query, or sometimes I look at the most similar one in my corpus, and then I respond with the following one from the corpus, because the similarity will be between terms, and then I want the reply. And the way we think of similarity can vary. So at the beginning, people would use TF-IDF feature vectors, but more recently we use neural net latent embeddings. Now moving on to generative chatbots. So Anthony covered this in his lecture on seek-to-seek, but this is a seek-to-seek model. And I just take an input, pass it through a seek-to-seek, and get what the reply should be. So for example, if the dialogue then I need to reply to is "How are you?" the model would just output "I'm good" and reply. This is an example conversation from BlenderBot, which is a chatbot from Meta AI. It's actually not a seek-to-seek model, it's an auto-regressive LM. And I feel like there's this trend recently where auto-regressive LMs and seek-to-seeks can be, like we can switch between the two. And again, pretty convincing conversation. I think this one would pass the Turing test. Maybe a bit silly. So it doesn't always go this way, right? Sometimes it starts saying the same thing over and over again. Sometimes it gives very terse responses and then also gets stuck. And there are ways to deal with these problems. So to get more diversity in the responses, we can modify beam search at inference time, or you can encourage diversity during training by including that in the objective. The issue of terse responses can be addressed by imposing minimum length constraints at inference time, and the issue of maintaining coherence across multiple turns can be addressed by more sophisticated training regimes, such as using RL adversarial training. Now, task-oriented dialogue systems. So this also have a long history going back to the GAS architecture in 1977. And currently there's a bit of a paradigm shift in the field where people are excited about using large language models for task-oriented dialogue systems and using alignment to ensure safety and make sure they do the right things. So I think it's easiest to juxtapose the two if we look at the cons of each approach. So frame-based ones are expert systems, so like old school AI, and they run into this knowledge acquisition bottleneck. So there tends to be a plateau to how evolved they can be because we need to encode information in each bot. And then for deploying large language models, that's also tricky because of safety concerns. And there's also a lot of discussion in ethical AI about bias, fairness. Uh, Now let's talk about the frame-based approaches in more detail. So we usually author a bot with a specific application in mind, and then each bot has an associated domain ontology. The ontology is a collection of frames, and then each frame is a collection of slots. So before we dive deeper into this, let's see a successful example of what this is from CAS, so this is back from the 70s. And I think it's pretty impressive. It does the task. It manages to book a plane ticket, I guess. And, it knows to ask for information about the time, offer alternatives when they are requested. Um, so yeah, like, this is the client is implicitly not accepting the suggestion, and then it gives another one. Um, it asks for follow-up information. It confirms at the end to make sure the client knows the booking was successful. So the way it works is based on the concept of frames. So I said a frame is a collection of slots. So let's see in more detail what it is like. It's this set of, in a frame, I need to find out where they are going from, what's their destination, when they want to leave, on what date, when they want to arrive, on what date. And so there's like multiple slots. They have different types. Here we have three types of slots. We have city, time, and date. And then also they use these question templates to extract information. So the very first iterations of these frame-based approaches had a simplistic dialogue policy that kept asking questions until it filled all its slots. Um, the language understanding was very shallow, so it just used rule-based approaches to fill slots. And also the dialogue was pretty boring, I guess, because it would just ask the same question over and over again if we didn't feel it. But it wouldn't rephrase or have more dynamic responses. Um, Currently, so even Alexa or systems used in production are based on this GAS architecture from 50 years ago. But they tend to be a bit more advanced, so people call them dialogue state architectures rather than frame-based. And they have these 6 components. So ASR and TTS are kind of at the beginning and end of the loop, and we talked about them earlier this week. And then the meat of a bot system is in this 4, I guess. So we have a language understanding module, a dialogue state tracker module, a policy, and a language generation module. So let's go through them one by one. The language understanding module does 2 main things. It does a utterance level task where it determines the intent. So in this case, if I'm, if someone asks me, oh, I want to fly, to SF on Monday, then they probably want me to get some options for them, some possible flights. And then also in the utterance above, they gave me some information about the date, the time, and the location. So these are slots I need to fill. Um, the slot filling task is done usually in this VIO or IOB, sometimes tagging. And what this scheme or paradigm says is that you look at each word in your sentence and you give it one of these three tags. So it's a seek-to-seek problem. And if a word doesn't give me any information whatsoever, then it's outside of any slot I care about. And then if it does give me information, it can be an B slot or an I slot. So the span of text, when the span of text that talks about the destination begins, that first word it gets the B tag because it's the beginning of the span. And then all following ones get the I tag. And then I do that for each slot I need to fill. So I have a beginning of the destination and the beginning of the departure time, and then also inside tags for each of these. And as opposed to frame-based systems that had rule-based parsers, modern ones use machine learning in specific points in this workflow. So the slot filling task is one of them, or you can use more fancy techniques. So one common approach is to train some kind of BERT system where we train an encoder to get good representations, and then at the at the final layer, or sometimes the second to last layer, we train classifiers on top of the hidden states to classify those tokens as being I or B. And also the intent classification task, so the one that's at utterance level, sometimes gets kind of thrown into this, where I use the CLS token or the end of sentence token and use that token's representation to train an intent classifier. Um, Now moving on to the next component in our architecture, we have the dialog state tracker. And what this does is it tracks the state of the dialogue as it progresses. So let's follow throughout this conversation. If the users, says this first utterance, then I know they are looking for a cheap place, right? And then as the conversation goes on, I know they want Thai food. I know they want the restaurant to be located in the city center. And then when they ask me this question, then I know they have requested the address and I can reply accordingly. And the way I decide when to request information or when to reply or when to maybe take some third type of action, um, the third component is in charge of this decision. So the dialog policy makes these calls, and its task is to look at the dialog history and decide on next actions. And sometimes to simplify things, they just look at the dialog state and the last few turns rather than the whole conversation. In more modern approaches, people use reinforcement learning to train policies, while at the beginning they used to be rule-based systems. So let's look at a case study of the type of problems the policy solves and appreciate how detailed they have become recently. So this is a simple example where I need to fill a single slot, right, from an utterance. And that's like the origin city, I guess. And I might want to confirm it, right? So I can explicitly confirm the slot, or I can implicitly do so by moving on to the next slot, but then repeating information about the previous one. So to formalize this, a policy might have different behaviors based on how confident I am about a slot value. So if I'm like really unsure about what I heard, then maybe I'll just pretend I didn't feel it at all and just request. And then depending on how confident I am, I might explicitly confirm the slot, implicitly confirm it, or just move on and not even ground a conversation, just assume I have it. Um, Now this is the last component in a dialogue system. It's the natural language generation one. So once the policy has decided, for example, I want to recommend, this restaurant in this neighborhood serving this type of cuisine, I need to decide how to phrase the reply to my user. And I can do so in multiple ways. So both these examples will be valid responses. Um, and NLGs are usually also machine learned, so trained from data. And because data is rather sparse for this kind of task, there's some pre-processing done when training. So in my train set that say let's sentence has sentences like this one, I'm going to replace all instances of a restaurant name with this restaurant name placeholder, and then train this like templated NLG system. And then at inference time, when I need to do a kind of recommendation, I will use the learned model to generate a templated sentence and then fill in the slots. Now, let's talk about recent progress in this field and large language models. So reinforcement learning from human feedback has made great strides in aligning language models with what human want them to do. And then you already talked about this. So this alignment process has three steps. First, we collect example dialogues, let's say, and then fine tune a language model towards a supervised policy. So here we kind of equate an instanceable language model with a given set of weights with a policy to talk about RL. And then in order to do RL, we need a reward model. So RL only works with like scalar targets. So we train this reward model using comparison data. And then we, we use PPO in the case of ChatGPT to uh, further fine tune the policy and get very impressive LLMs such as ChatGPT. So this third step, the RLHF step, it optimizes this type of training objective. And all this says is that I want to maximize the reward, so alignment with human preferences while minimizing this KL term, which has this expression. We don't need to look into it too much, but it's basically a measure of how far away the policy has strayed from the original language model. And the reason we want to have this regularization is that if we don't, then we'll get the generate policies. So this example, it doesn't actually use PPO, it uses reinforce, and there's no regularization here. And the reward is just to say Paris once. So there was no reward for like saying Paris like a million times. But the policy will still degenerate, and the LM would just kind of keep saying Paris and nothing else. So, all right, and also this discussion is inspired by this blog post that is in turn based on an EMNLP paper. So before we talk about what the blog post says, this is a Bayesian inference interlude, because I'm going to talk about a correspondence between RLHF and Bayesian inference to get more intuition about what this like mysterious RLHF really does. So the interlude is that in Bayesian inference, we start from a prior. So in our case, this would be the initial language model or the initial policy. And then we observe some likelihood, which in our case is related to the reward model. So it's like how good the model is. And then, we get a posterior, which is how we want to like update our data. So what this blog post and the associated paper do is they posit there is some ideal policy that looks like the Bayesian update, right? So this is the prior, and then the reward model gives me the likelihood of being aligned with human preferences or having a good LM. And then this is just some normalization to make sure this integrates to one. And you can actually show that this type of expression is what you get when you optimize the training objective. And moreover, you can show that the training objective is not only just in terms of the reward and staying close to the original policy, but also it's a formulation of how far away I am from the ideal policy. So as we optimize this term, the training objective, we actually move closer to the optimal policy. Now some case studies. So I think there's a lot of excitement about using LLMs in dialogue systems. So I was playing a bit with, going back to the original like qualities of human conversation and why it's hard. We said that, the sub dialogues are hard, corrections are hard, the dialogue state tracking is hard. And this is just playing with ChatGPT. So I hope you can see. Um, So let's say in this dialogue where I change my mind about the time. Well, first it refuses to answer, which I think is maybe good because it shows they've addressed safety pretty well. And then when I nudge it a bit more, it does the language understanding pretty well, so it gets the correction, right? Um, and then it also knows, like it seems to understand what happened and do the dialogue state tracking in a simple case. Um, Also, again, when I contradict, it knows the most recent information provided. Um, this is the same idea where I introduce more people, so it needs to keep track of me and my mom and Maria, and it seems to do that pretty well. Uh, so yeah, it knows. And also it's like a multi-turn situation where, I give some information, then I enter a sub-dialogue, then I correct the information given a few terms before, and it knows that I've corrected the age given like a few utterances ago. So that was pretty impressive, I think. Um, Now, I think a lot of criticisms of large language models in the form of they don't have common sense, they don't have access to knowledge bases, they hard to integrate into systems. Knowledge cutoff, right? So if you play with ChatGPT, it doesn't know the queen passed away, it doesn't know about the recent events. And I wanted to show you some cool things people are working on to address this kind of problem. So this is an open source project called LangChain. And it's supposed to integrate LLMs into software systems. So uh, I guess their statement is, they want to do QA over catalogs of data documents. They want to, build chatbots, which are entertainment oriented and not that hard to build with LMs. And they want to build like task oriented systems or agents. Um, and they have some cool utilities for that. So they do some kind of version control for prompts, which I think is exciting to think about moving forward because people say, prompts are becoming part of software, I guess. Um, they integrate outside documents. They have chains, so instead of using just one LM, you can combine them and have them cooperate to solve a task. They introduce memory, which I think is very cool because ChatGPT has a limited context size. It's pretty big, it's at what, 8K tokens. but still, it seems like summarization and memory are important in building robust applications. And also, I think this is a really cool idea where they want to use LMs to evaluate LMs because yeah, it does seem hard to evaluate their performance. So now let's play with this application. So here I wanted to, retrieve some information, and I want to also do a math problem, which are both notoriously hard things to do with LMs. And what they propose is to integrate APIs. So this is like a Google Search API, and integrate outside tools. So this actually is linked to a Python interpreter. And let's see if it can do it. So this was pretty great. The math is correct. It's actually not ideal because they actually broke up recently. I think she's dating Harry Styles now. But in this model's defense, if you Google who Olivia Wilde's boyfriend is, Google says it's Jason. So I could make the same mistake. Um, Now let's look at seeing how far I am from MIT and how long it will take me to walk there using the same tool, so the Python REPL and Google search. Oh yes, thank you. That's very kind of you. So yeah, so if you've this is interesting to point out. So if you've been following a literature, chain of thought prompting seems to be an exciting approach to getting these things to work well. And it seems like this library achieves that. So you can see that the system is like breaks the task into subtasks and then tries to solve each one. So it's like, oh, I need, and then this is a thought, right? It's like I need to do this subtask first. How might I solve it? And then it will choose one of its tools. So in this case, it's like, oh, let me do Google search. And then this is the input to the Google search. And then this is the information that comes back from Google. And then also it's like, oh, okay, now what's Jason's age? And then again, Google search can help me out. So let's ask this API. And then for this math problem, it's like, oh, let's ask the math calculator, which is actually a Python interpreter. Um, Now, in this example, so also using Google and the Python thing is like, um, how long it will take me to go from LA to Boston. Um, and, the first task seems to be to know the distance between LA and Boston. So it Googles that, gets it right. And then this is a bit um, suboptimal, I think, because it sets out to know how many kilometers I can walk in a day, which I think implicitly to us means like if I really want to get there, and I would walk all the day. But then I guess the action input is phrased vaguely, and then it gets an average rather than a maximum. So then, it looks like it will take me a very long time to get to Boston. And it's interesting to see that using different tools results in different qualities of the system. So if I use Wolfram Alpha instead of Google search, let's see what happens now. So again, guess the distance. I guess it went astray. Uh, all right, well, yeah, I guess it's a similar result in this case. Sometimes different tools have different results. All right. Well, that's actually all I had. Do you have any questions? And then we'll talk about the exercises and last week's answers. Yes? When you say math problems, you mean like large numbers or you mean like complex, like difficult? Yeah, I think that's true. Yeah, I think ChatGPT tries to do it. Oh, thank you. So the question is, um, I guess a comparison between this and ChatGPT's approach to complex questions that need multi-steps reasoning, right? And yeah, I think this approach helps a lot, right? Because it encourages it to break the problem into thoughts and then, so this would be like subtasks, right? And then address each one. Uh, so yeah, I think it's similar to the let's think step by step approach from a few months ago. Ah, that's very interesting. Yeah, so Cole is referring to this, I think, Google paper that applies formal proof techniques to LMs, where when solving a complex reasoning task, instead of going forwards from the problem statement with the answer, it tries to go backwards, which is a lot of how I did PSETs. So I think it makes sense, but it does not actually. Yeah. So this would be a cool augmentation of the system. So I feel like I feel like I start like from both directions, and then it makes the branching smaller, right? If the depth is half. Yes, I can. I'm a bit nervous, but let's see what happens. It does, yeah. Let's do. Nice. Thank you. So for next time, so going back to frame-based systems, so I showed you like kind of like BERT for slot parsing. think daytimes are a bit different from most type of slots, so it would be interesting to look into how to parse those. And then this is a classic and talked about a lot on Twitter. So you should read a bit of lesson. It's 1K words. It's like half an hour read. And then last time exercises. Do you wanna present them? Thank you.
These are the solutions to last time's TTS questions. The normalization of this sentence we convert into a series of words. Louis the 11th, Rose presidency, $1,911.11 in the year 1911. So the comma here, comma there are treated differently. The xi here and xi here treated differently. 1911 here and 1911 here are treated differently. So you need to be careful. And then for the speech generation task, it depends. This is what I came up with.
Execute order 66.
So I'm not sure whether the virtual audience can hear that, but okay.
It's small. Could you volume up?
Okay.
The time has come. Execute order 66.
So that was
Awesome. Thank you.
American accent. And then for the comparison question, well, general ASR generally needs to recognize many different accents and many different speakers. So it has a lot more parameters, typically maybe 10 times the size of a TTS model that only requires to produce one speaker voice. And it also requires many more data, like 1,000 hours of data to train a reasonably good general ASR, whereas TTS only takes about several hours, like 20 or 30 hours of data. It would give you a reasonably good TTS, and it also trains in a much shorter time frame. So that's the solution.
Thanks, everyone.